So any questions about the stuff we've done before? Okay. So we talked about scientific notation. And we talked about using this, again, large numbers. We're going to be using a lot of large numbers. So you can't put that number into a calculator. So it's 6.692 times 10 to the minus 24th. So you need to become familiar with your calculators, how to do that. Depending on your model, you do it different ways. Excuse me. So looking as examples, what would the top one be? Tell me in scientific notation what that would be. 1.8 times 10 to the what? Okay. So we're going to move the decimal point over. 1, 2, 3, 4. This line. So we get 1.8 times 10 to the minus 4. Second one, what would it be? No. We first are going to have to move the decimal point over, right? So we're going to move it over 1, 2, 3. So we're moving it 3 spots, so we know it's times 10 to the third. So what does the coefficient have to be? How many significant figures here in 3, 4? So how many significant figures have to be in the coefficient? 4. So this is 3.004 times 10 to the third. The next one. Okay. 3.00 times 10 to the second. Because we have 3 significant figures here because there's a decimal point.
So how many of the significant figures you have, that's how many?
Have to be in the coefficient. The bottom one. Yes. One, 2, 3, minus 3. So are you okay with that? Everybody okay with changing things to scientific notation? Okay. Talking about accuracy and precision. When we're doing measurements, we want to be accurate and precise. What's the difference? Accuracy is the degree of agreement between the true value and the measured value. Error is the difference between the true value and our estimation. And there's 2 types of error, random and systematic. Precision is a measure of agreement of replicate measurements, and deviation is amount of variation present in the set of replicate measurements. So here we're shooting at this target. Target A, we took 5 shots, what they call tight grouping. So our repeatability between shots is very good. Okay? And are we on target? Yes. So we have good precision, good repeatability, and we're very accurate. B, we have good repeatability. All our 5 shots are close together, but we're not very accurate. We're far from the target. And the bottom one here, we're imprecise and inaccurate. We're all over the place. Now, what causes this is error. And there's random error and systematic error. So let's say you're working at a gumball manufacturing company, and your job in quality control is to weigh the gumballs. And they all have to weigh 2 grams. So you come in the morning, and you start with a box of gumballs. You have a balance. Balance starts off at 0, and you put the first gumball on. 0.95 grams. The second one is 0.98 grams, and then it's 1.1 gram. And you do this all day. Okay, and all of a sudden you put a gumball on there. For some reason, it's got a little growth on the side, and it's 1.8 grams. And you go around, and the rest of them are around 1 gram, plus or minus maybe 1/10 of a gram. So what about the one that was 1.8? What do you say about it? There's a source of error. Do you know why it's 1.8? Can you predict? Can you tell me what's wrong in your process? Or is it just something that happened?
Like every 15th one or something.
But I mean, if you just see it, it's a random error. It occurred, you don't have a clue. Okay, so next day you come in, you sit down, and you don't set the balance to 0. So it's actually starting out at 0.2. So everything you weigh, all the weights you're getting, may be precise, but they're 0.2 grams too high. Why are they 0.2 grams too high? Yeah, so it's a systematic error. We could say everyone is off by the same amount because you could trace it back and say, because I didn't put the balance at 0 to start with. So in bioprocessing manufacturing, and that you look for systematic errors. In pharmaceutical manufacturing, okay, if the tablets, you measure the size is continuously off for that whole lot, you look and you see what you set the press at. Maybe you were offsetting the press. If all of a sudden you see a tablet that's broken in half and the rest of them are fine, that's sort of a random error. You don't know what happened. A lot of times we have to find errors. You know, something goes wrong. When I was doing troubleshooting, something would go wrong, and they would say, what happened? And you could go back and say, well, you had a leak in your tablet press, was leaking oil in there. Sometimes you'd find stuff, you don't have a clue. You find a piece of metal in there, you couldn't trace it back to anything in the production process. So it's a random error. Or a piece of plastic. Found a piece of plastic in there one time. Well, there's nothing in the process until later on one of the technicians confessed that he was bending over the vat and he dropped his pen in there. Pen cap came off. So now we talk about significant numbers. What about exact and inexact number? How can a number be inexact? Well, inexact numbers have uncertainty. So anytime you make a measurement, length, width, weight, volume, there's some uncertainty to it. We already talked about that because not using an accurate enough ruler, I can guarantee you when you do labs, you're going to see on the balance, the last place, the milligram place, because of drafts and that, it's going to be bouncing up and down a little bit. You know, what do you do for the donation thing? So you're just drawing samples, right?
Yeah, but I work in the lab also.
Yeah, but when you draw samples, you have the little tube, you push the vacuum tube in there, and it takes a certain amount of blood, right?
Yeah, it's on the time.
But you don't take the exact amount every time. No, pardon? Well, because you don't have a way to measure it, but yeah. So there's some uncertainties. The protocol may say take 5 milliliters, but you fill up the tube X amount. So exact numbers are consequence of counting. If I count the number of people in this room, I'm going to count on this, 26. So I know there's exactly 26 people in this room. There's not 26.2 people. There's not 25.8. There's exactly 26. So that's an exact number. And by definition, it's an exact number. 12 inches in 1 foot. Not 11.8 inches, not 12.2 inches, exactly 12. So anytime you have a number that's a definition, that's an exact number. And exact numbers are considered to have an infinite number of significant figures. So when we're doing calculations, you don't look at exact numbers. Just look at the inexact numbers. Rules for rounding, and these are things you've learned a long time ago. When the number to be dropped is less than 5, the preceding number is not changed. So like 13.4 would round off to 13. 5 or more, it's rounded up. 13.5, 13.6, 13.7 is rounded up to 14. All right, so 3.34966, this should be times 10 to the 4th. If you round it to 3 significant figures, you would go, okay, here's the first one, here's the second one, here's the third one. So I'm going to drop everything after this. But this is a 9, so it would be 3. I have to round this one up, 3.35 times 10 to the 4th. So 61.40 rounded to 3 significant figures would be 61.4. 6.171 would be 6.17. 0.066494. Three significant figures. Is this significant? This? No. Leading zeros are never, ever, ever, never significant. If they're in the front, you ignore them. So this is significant, the first 6, the second 6. This is our third. This is a 9. So it's 0.0665.
Oh, so the second 0 would be significant or no?
No. How many significant figures I have here now? 3.
Okay.
All right. Questions? Because we're going to start doing calculations, and you have to know how many significant figures have to be in your answer. For addition and subtraction, the result in the calculation cannot have greater significance than any of the quantities that produced the result. So here we have these 4 numbers. Oh, if we're going to add these four numbers, and I don't know what the number is, our answer can't have any more decimal places or places after the decimal point than the number with the fewest decimal places. So this one has 2, this one has 5, this one has 3, this one has 5. Our answer has to have 2 decimal places. So you do the addition on your calculator, whatever that adds up to, and then round off the 2 decimal places for addition and subtraction.
On the book, they had, see those first 3 numbers?
Yeah.
They had the same example, it's just that they got those first 3 numbers added up to equal that fourth one. You know what I mean?
Oh, they had this. Okay, I see what they said.
They had the final answer was 152.82.
All right. So if you're adding these, this would be the answer. 2 decimal points, this would be 152.83. Oh no. 83. I can't tell what's in the book, is it? So how many decimal points would be in the answer here? Bottom one. 1. Be very careful when you're doing addition subtraction. Well, let me go back. We'll go on to the next one. Page down. If you're doing scientific notation, there's 2 ways to do it. You can convert them both to standard form and do it, which can be a pain if they're large numbers. One page down. Or change one of the exponents so that they're both the same. So 9.47 times 10 to the minus 6 changes to 0.947 times 10 to the minus 5. If you make this number smaller, you have to make the exponent bigger. Okay? Now you can add these 2 together. The exponents, which really shouldn't be a problem with you. You do it on your calculator, it'll do it automatically. For multiplication and division, the answer can't have any more significant figures than the measurement with the fewest significant figures. Oh, now all of a sudden the exponents are working on this thing. Okay, so here we have 4.2 times 10 to the third times 15.94 divided by 2.255 times 10 to the fourth. And you do this all on your calculator, and this will just get 2.96886918. Do not put that answer down. How many significant figures here? 2. How many here? How many here? 4. The answer can't have any more than 2 significant figures. So you have to make this 2. So 2, 9. This is a 6, so I have to round the 9 up. It becomes 3.0. So let's do this problem. No, 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 no. What happened to my pen? Cross all that out. tell me what the answer is with the correct number of significant figures. It's all addition. You saying 12? And you're saying 12.3? I know, I heard you. Yeah, we got you in the 12. I'm taking a poll. Okay. And you're saying 12.3 over there? All right. Let's look at it. 6 and 1 is 7. 12, carry the 1. 8, 3. So that's what you got in your calculator, right?
Yes.
All right. How many significant figures? How many significant figures? How many significant figures? Answer has to have no. Addition, it has to have the same number of decimal points. 12.3. Yep. So you only have one decimal point, so it's 12.3. I do that because usually half the class comes up with 12, because I just got doing multiplication and division. There you use the least number of significant figures. Addition and subtraction, you use the fewest number of decimal places. So don't get caught by that. Oh. Okay. Very important topic. If you can learn this, you'll be successful, I dare say, through most of the course. Unit conversions. The factor labeled method, also known as dimensional analysis. If any of you are in the nursing programs, you go into the nursing school, it's also known as dose calc. So we use conversion factors to convert from one unit to another within the system, or from one system to another. And you do it all the time. You don't realize the process, but you've been doing it your whole life. And I know in the back you're thinking, yeah, that's what you said about smelling stuff too, and that didn't work out too well. Okay. So, how many quarters in a dollar? 4. $3. How many quarters do I have? 12. You did that in your head. So you did unit conversions. You did factor label method. You did dimensional analysis. You didn't know you were doing it. And you did a process in your head. You probably didn't realize the process because no one told you you were doing a process. But once I show you the process, it's the same no matter what you're converting to anything else. You start with an equality. You made an equality between quarters and dollars. Here's an equality between gallons and quarts. 4 quarts is 1 gallon. Okay? We all know that. So then you make a conversion factor. Actually, you make 2. 1 gallon for 4 quarts, or 4 quarts for 1 gallon. So those are ratios. One's the inverse of the other. Those are called conversion factors. And they didn't. So let's go back. I think I read on that page easier. They wanted to know, was it 12 quarts to 1 gallon? Pardon? No, on the next page. They're converting 12 gallons to quarts. Okay. So you know the relationship between gallons and quarts. Do conversions, unit conversions. If I have 12 gallons and I want to know how many quarts, I know you could do that in your head, but we're going to walk through the process because later on we're going to change numbers and units. You start with what you know. 12 gallons. And I put it over 1, and you might not see that in your book because when you're going to do this on your own, you're going to put it on a piece of notebook paper, and if you write the 12 on the line, it'll end up in the denominator rather than the numerator, and you screw up your calculations. You want to find out here how many quarts. So now I'm going to multiply this by some conversion factor. I have to get rid of the gallons and keep the quarts. So those are the factor labels, the gallons and the quarts. So if I want to cancel the gallons, what's on the top here goes to the bottom here. And I'm going to quarts. So that goes on the top. Now I look at my two conversion factors. Which one has quarts on the top and gallons on the bottom? The second one. I put those numbers in. 4 and 1. Now I do plug and chug. 4 times 12, 48. Any conversion, that's how hard it is. As long as you have the qualities. Now, if I said, how many pints in a quart? A lot of bakers in here, I can tell. All right. As far as I know, it's 2 pints to a quart. So now, my problem is I have 6 let's say 6 pints. How many gallons is that? Well, again, I'm going to start with what I know for that problem. So I'm going to start with 6 pints. I'm going to abbreviate it as P over 1. And I want to find out how many what happened to my pen? Gallons I have at the end. Do I have a conversion factor between pints and gallons? I do. I don't. I have one between pints and quarts. Yeah, exactly. I can go from pints to quarts, and I can go from quarts to gallons. Because those are the relationships I know. So pints, I know I can go to quarts. I'll put the pints down here. And then from quarts, I can do the gallons. You can see factor labels, the quarts cancel, the pints cancel. Now I go over here. 1 quart is 2 pints. 1 gallon is 4 quarts. So now I do 6 times 1 times 1 divided by 2 times 4. So 6 divided by 8 is... I thought you were doing what? Well, 0.75, right? Okay, if I had 6.0, 1.0 in that, it would all be... But since I don't have one significant figure, what would it be? 0.8. So I had to use 2 conversion factors. Later on, when we get to stoichiometry, you might have to use 3 conversion factors. But as long as you have the qualities, you can change anything, convert anything into anything else. This is the process. So whether I use dollars, nickels, pints, quarts, grams, moles, atoms, I can, as long as I have an equality, I can make a conversion factor. If I can make a conversion factor, I can convert it to anything else. As long as you set it up right, it shouldn't be a problem. And basically, this is what we did. All right, convert 360 feet to miles. The relationship is 5,280 feet to miles. So the conversion factors, we got 2, 5,280 feet per 1 mile, or 1 mile per 5,280 feet. Again, start with what we know in the problem, 360 feet. What we want to end up with is how many miles that is. So I'm going to multiply that with a conversion factor which has miles on the top, feet on the bottom. Looking at our units, the 1 goes up here, 5,280. 0.6 something? 0.067? Yeah, 0.0. It's 0.067 what? Oh, you say 0.07. How many significant figures there? No. The leading zeros are never significant. So it would be what? There you go. I know, but it's good. Make the mistake now. Don't make it on the test. Pardon? 360 divided by 5,280. Oh, the answer is 0.068. But he said 2 significant figures. This is only 1. So, no, it's not this. So here is a multi-step conversion. Convert 0.0467 kilograms to milligrams. All right, and it's not 1 to the third. 1 kilogram is 10 to the third grams, or 1,000. And 1 gram is 10 to the third milligrams, or 1,000 milligrams per gram. Yes? No. You got to know it from the problem. Let's go back to that one. That's a good question. Oh. Actually, I don't think I'll have to do. Oh, it's still saved it. So how many significant figures are here? 2. There's no decimal point. How many here? No. 3. There's no decimal point there. So my answer has to be, since I'm doing division, it has to be 2. And if you do it on the calculator, 0.068 something, 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 something. So 2 significant figures, 0.068. Okay? All right. So here we're going. So again, we're going to start with, ignore this down here because this is all 0.0047 kilograms. Put that over 1. We want to know eventually how many milligrams. We can't go from kilograms to milligrams because we only have kilograms to grams. So we go to grams over kilograms. All right, come on. Oh no, this is wrong. Okay. Over kilograms. Then from grams, we can go to milligrams. Jesus. Okay. Scratch that. Grams over kilograms. Then we can go to milligrams over grams. So we know 1 kilogram is how many grams? 1,000. 1 gram is how many milligrams? 1,000. So it'd be 0.0047 times 1,000 times 1,000. So it'd be 4.7 times 10. 1, 2, minus 3, 10 to the third. 4,700. Sorry about the board messing up like that. So quick review. 0.0047 scientific notation is what? 3. We're going to multiply that by 1,000 in scientific notation is what? Times 1 times 10 to the 3. When you multiply exponents, what do? You add them. So I have 4.7 times 1 is 4.7. 10 to the minus 3 is 10 to the 0. 4.7 times 10 to the 0 times 1 times 10 to the third is 4.7 times 10 to the third. And don't forget, these are exact numbers, so they have infinite number of significant figures. Yes? No? Oh, lost? Oh, okay. Is everybody okay with this? Okay. When you multiply in scientific notation, you multiply the coefficients first. 4.7 times 1 is 4.7. The exponents you add. So minus 3 plus 3 is 0. So then you're going to multiply the 4.7 times 1, which is 4.7 again. 10 to the 0 times 10 to the third is 10 to the third. All right, there's some practice problems. We're not going to do them here because because you'd have to look up the conversion factors. 1 inch is 2.54 centimeters. Then you'd have to look at how many millimeters in a centimeter? How many millimeters in a meter? How many centimeters in a meter? So how many millimeters in a centimeter? 10. The difference between millimeters and centimeters is a factor of 10. Then milliliters, the pints, you'd have to look. There's a table in your book that has conversions.
So they're going to be one of the tests that.
Yeah, but you'll have an open book, so you'll have them right there. Temperature. Okay. If you hadn't realized, the temperature is the degree of hotness of an object. So there are 3 temperature scales that people use. Fahrenheit, which is what we use every day. Celsius, which is what we're going to use in here every day. And Kelvin, which we'll use part of the time. You notice Celsius and Fahrenheit are degrees C and degrees F. Kelvin is just K. No degree symbol. Kelvin relates temperature to molecular motion. Comparing some things, body temperature, 98.6 Fahrenheit, 37 degrees C, and 310 Kelvin. Freezing point of water, 32 degrees Fahrenheit, 0 degrees Celsius, 273 K. Absolute zero is 0 Kelvin, which is minus 273 degrees Celsius. Absolute zero is the temperature at which all molecular atomic motion stops. That's the coldest it could ever be. What? For what? Absolute zero is 0 Kelvin, which is 273 degrees below 0 Celsius. Okay. Degrees Fahrenheit is equal to degrees Celsius times 1.8 plus 32. Degrees Celsius is equal to degrees Fahrenheit minus, minus 32 divided by 1.8. So if I have minus 40 degrees Fahrenheit, what would it be in degrees Celsius? do, 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 do. What is it? What do you mean you don't know? You got a negative 40? Yeah, negative 40. That's right. That's the one place on both scales where they overlap. I always put that up there because I watch people and they do the calculation. They go, it can't be negative 40 because we started with negative 40. Yeah, that's the one place where they're both the same. So we're not going to do a lot. Yes. No, you're multiplying. Then you add the 32. Yeah. So we're not going to do a lot of Celsius to Fahrenheit conversions, but we do a lot of Celsius to Kelvin later on in the semester, and Kelvin to Celsius. So, do you have to know it? For what? Celsius to Kelvin? Oh, that's easy. I'm sorry. Kelvin is degrees Celsius plus 273. Does your book 273.15? Okay. The book uses just 2.15. So Kelvin to Celsius would be minus 273.15. So, like I said, Kelvin is related to molecular speed. So as the Kelvin temperature increases, molecular speed increases. And that has a big effect on what's called kinetics, rates of reactions. Energy. It's the ability to do work. Two types. Potential energy. And then kinetic energy. Usually it lands with a bigger bang, but kinetic energy is the energy of motion. If you look at a dam, the water behind the dam is potential energy. If the dam breaks, you're going to see a lot of kinetic energy, briefly. Okay. So potential is stored energy. We also categorize energy by its form: light, heat, electrical, mechanical, and chemical. The law of conservation of energy says energy cannot be created or destroyed, merely changed in form. So you can take mechanical energy, change it to thermal energy. You can take electrical energy, change it to light, change it to heat. You can go back and forth. But you can't create new energy, and you can't lose it. Go somewhere. Energy conversion always occurs with less than 100% efficiency. If it was 100% efficient, you could power your whole home with a 9-volt battery. But we lose it. Obviously, you make toast in the morning. The toaster converts the electrical into heat. All chemical reactions involve either a gain or loss of energy. So everything eventually balances out. Which is why at the beginning when I did the introduction, we talked about green cars, electrical cars, energy consumed in one area is released in another area. Question is, where do you want to make your expenditures? The basic unit of energy is the calorie or the joule. 1 calorie is 4.18 joules. So there's a conversion factor right there. So you can change calories to joules and joules to calories. A kilocalorie, there's 1,000 calories in a kilocalorie. It's also what's called a food calorie. Notice when we go to food calories, it's a capital C. Capital C means food calories. The little c is chemical calories. So when you look at your Snickers bar and it says contains 250 calories, those are food calories. It really contains 250,000 chemical calories, which explains why you have to run 45 minutes on a treadmill to use up the calories from eating a Snickers bar. 1 calorie is the amount of heat energy required to increase the temperature of 1 gram of water 1 degree Celsius. So if I have 1 ml of water at 25 degrees Celsius and I heat it to 26, I've used up 1 calorie. Okay? Questions about calories? So remember those conversions. You don't see it. 43?
There's nothing in, I don't see the part about the calories.
Okay, I was looking at units of energy.
You don't have the conversion unit in your book?
Don't have the food calorie conversions in the book.
The conversion table might be in a different place.
Between the calories and the kilocalories? Oh. Okay, it's on page 30 under humanist perspective, food calories. And under page 29, it goes through 1 calorie is 4.18 joules.
Yeah, my book started with accuracy and precision.
Let me see your book.
Oh, yeah, I see it.
What page is it in your book, in the small book?
Page 43 was.
Okay. It's on page 43 in your book. Energy. And then on page 44 under food calories, it talks about food calories. PowerPoints are listed on Blackboard. Which look a little bit different than these. These aren't Smartboard, which converted from.
But these PowerPoints are available on Blackboard.
Yeah. Just click on the Blackboard thing and PowerPoints and. In fact, I encourage you, if you can print out the PowerPoints, and print like 6 to a page because you don't want 2 million PowerPoints by the end. And put your notes on them rather than trying to thumb through your book. What are these we got to go? So, 59, 60. Okay. Okay, I think we're going to stop there at whatever we have. Slide 60.